Hello, good morning, good afternoon, good evening, and welcome everyone. It's an honor to be here with you today. I would like to make a short presentation about numerical investigation of condensing flows in a supersonic separator. First, let me introduce myself. My name is Ulisses Costa, a PhD student mechanical engineer at the University of São Paulo. I am a researcher at the Research Center for Gas Innovation. Currently, my research lines are concentrating metastable condensation, CFD, and machine learning application. Let me start by giving you some background information. One of the challenges for the development of natural gas reserves is to remove contaminants from the mixture to make it economically attractive. Today, the separation of these contaminants is done by membrane separation plants, but these equipments are costly, waste a lot of energy, and occupy an important area of the production unit. In supersonic separation, an innovative technology based on the adiabatic cooling of a swirling gas flow, ARISE has a promised new technique to remove water and hydrocarbons from natural gas. However, the process of condensation in a compressible flow is still poorly understood. As a contribution to overcome the condensation challenges, the main objective of this work is to improve the numerical accuracy of an open-source CFD to correctly capture the occurrence of a condensation wave in the nucleation process. Now, I would like to show you an overview of the methods and models using in this study. The nucleation is the first step in the formation of a new thermodynamic phase. The first thermodynamic approach to the nucleation process is due to the American scientist Josiah William Gibbs, who demonstrated the numerical theory of curved surfaces. In this work, it became clear that the work required to form a single spherical doublet is equal to the change in Gibbs free energy during the process and consists in a volumetric term and a superficial term. The other S represents by the supersaturation and is the inability of a fluid to condense when saturation conditions are reached in an expansion. For condensation to take place, it's necessary that the doublet radius be larger than the center value, which is commonly referred as the critical radius. Most condensation simulations are based on a nucleation rate and a doublet growth rate models. Some of these models using this present work will briefly present now. The first theory of condensation phenomena is the classical nucleation theory, CNT. It assumes that the liquid doublets are all spherical and the vapor phase and liquid phase have the same temperature. Although the CNT was able to predict the occurrence of condensation, it failed to predict it accurately. Therefore, several corrections have been proposed to this theory. One of the corrections proposed to the CNT is the no isothermal correction. This proposal drops the assumption that the vapor and liquid phase have the same temperature. Another nucleation rate model is the one proposed by the internally constant classical theory, ECCT model, using kinetic theory to improve the accuracy of the equation. And the last equation is the factor F correction, which adapts a factor F to the exponential term in the equation. The F factor was determined using experimental data, and it corrects the value of the Gibbs energy barrier. Most condensation models are based on modeling the nucleation rate and the growth rate. However, these models do not express the evolution of the liquid phase or the distribution of the doublet radius. One of the possibilities of doing this is by the so-called method of moments. It's important to understand that the nucleation rate studies the evolution of doublets until the formation of a single cluster. However, inside a nozzle, there is a population of doublets, and for this reason, the method of moments is the most suitable for this numerical investigation. The great advantage of the method is that it can be easily executed on microcomputer due to the low computation cost. It's not part of the scope of this presentation to develop the algebra behind this method. we can see the set of equations that represents all the moments below. The physical meaning of each moment can be seen in Table 3. Let's turn our attention now to the numerical results. All simulations are performed in CFD open source code Stanford Universe Unstructured, SU2 or SU2. Turbo two-phase is a branch developed by research from Delft University. Was used for the calculation of the two-phase flows. All meshes of this work are generated using GMesh software, an open source neat element mesh generator. The well-known Mosenstein nozzle was used in test case B. The nozzle geometry can be seen in Figure 4. The Figure 5 shows the results for a set of numerical experiments. For this study, the experiment 4024 was chosen. In our simulation, we have adopted the Penrose-Valor equation of state, and all the calculations are performed on a 50,000 cell grid. The set of boundary conditions for the simulation was summarized in Table 2. Figure 6 represents the numerical result for the moment of order 0. The blue region represents the absence of water droplets, and to be clear that droplets only appears after the condensation wave. It's important to note that initially the branch had only the classical nucleation rate model, CNT. The author of this work introduced two other models in the code, ECCT model and the correction factor F. For the purpose of illustration, the Figure 7 shows a comparison of the results obtained for each nucleation rate model with experiment 2024, represented by the red dots. Through a quick analysis, it's clear that the new nucleation rate models implements are more accurate than CNT. The correction proposed by CCT model, represented by the dotted grid line, increase the accuracy of the capture of the condensation wave. Although the system model shows significant improvements over the CNT model, it is still overstating the value of the droplet population. The last simulation, represented by the blue line, shows the correction factor F captures a condensation wave very close to the points that represent the experiments of Mosenstein. The Figure 8 represents a comparison between the zero order moments for different nucleation models. As previously stated, the moment represents the total number of liquid droplets per unit mass of mixture, and its result is intrinsically linked to the nucleation rate. When you compare the zero order moments of each model, the numerical difference becomes evident. In CNT model, nucleation starts upstream at point x equal 9.25 centimeters, while for the system model, nucleation starts downstream at point x equal 9.68 centimeters. The numerical values of both models for the zero order moment are not very different. However, when comparing them with the model that was corrected by the introduction of factor F, one clearly notices a significant decrease in the zero odd moment value. For a better understanding, the Table 3 shows the position difference between the numerical results obtained with the simulation. In test case B, a three-dimensional simulation of condensation phenomena was performed using a new mesh with 5 million cells grid in order to test the efficiency and accuracy of the code for three-dimensional meshes. The 3D model of the nozzle, which shows the moment of order 0 along the length of the nozzle, is shown in Figure 9. It's already been pointed that the occurrence of condensation leads to an increase in the flow static pressure. This is illustrated in Figure 10, which shows a pressure of stagnation pressure. slice. The flow static pressure is decreasing continuously when there is an increase in static pressure due to the occurrence of condensation. Figure 11 shows a slice the moment of order 3, which represents the wetness fraction. As was the case of figure 5, change in the moment of order 3 can only be seen in the divergent section of the nozzle, where condensation occurs. And here we have a nice image of the condensation wave. Let's talk about the conclusion of this work. The numerical results show that SU2 or SU square solver is capable of successfully simulating the condensation phenomena for two-dimensional or three-dimensional problems. The Hill methods of moments provides reasonable, accurate prediction, especially when associated with a correct nucleation rate. I would like to thank you for your attention to this presentation. If there is any doubt, please don't hesitate to send me an email. Thank you.